Welcome back to the world of submodularity. I hope you enjoyed learning about MCMC this morning. It was very important. It's a very important topic. Almost as important as submodular functions. Not quite. But it is something that you should definitely know about. And actually, I have to admit that there are some commonalities between MCMC and submodularity, which, unfortunately, I'm not going to talk about today. But indeed, there are some things that they have in relationship to each other. So maybe what we should do is start, once again, with the definition. So here's the definition of submodularity. This is from the perspective of the matrix rank function. What I'm not going to talk about is the matroid rank function. But a matroid, as I said yesterday, a matroid is something that generalizes a matrix rank. And it's an algebraic object that corresponds to a form of independence that is strictly more general than a matrix independent set. So what I wanted to start talking about, however, is some of these submodular properties. Like some of the ones that I think are somewhat interesting, I'm not going to talk about all of them, are things like you can take submodular functions and combine them together and you preserve submodularity. For example, submodularity is closed under conic combinations. And this is something that, of course, we utilized when we talked about the applications yesterday for learning mixtures of submodular functions. And we use this fact here by making sure that the coefficients alpha are all non-negative, that we're guaranteed that that combination is submodular. So conic combinations of submodular functions are submodular. Similarly, something else that we also implicitly used was this notion of restrictions. So we defined the graph cut function. And if you remember, there was one slide from yesterday that talked about the graph cut function, but on the bottom part of that slide, it talked about a sum of a number of submodular functions. Each term in the sum corresponded to an edge in a graph. And for each one of the terms in that sum, you had a submodular function restricted to the two vertices corresponding to that edge in that graph. So it's a sum of restrictions. And a restriction essentially has this form. This is just one individual restriction. So restrictions preserve submodularity. Sums of submodular functions preserve submodularity. And so therefore, sums of restrictions preserve submodularity. And so a graph cut function is essentially one that can be represented as a sum of restrictions associated with the edges of a graph. And I should mention also that if you have a hypergraph rather than a graph, where edges comprise more than two vertices of a graph, then the same thing applies. You just restrict it to, rather than two vertices, you restrict it to the set of vertices that comprise the hyperedge in the hypergraph. Another form is conditioning. So if we can sort of define a new submodular function by conditioning on C. Now, conditioning is sort of a terminology that comes from conditional entropy. And really, we can even notate it in the same way. F of A given C. So sort of if we know C, or if we're conditioning on C, or if we're insisting upon C being on the set, but we want to renormalize by subtracting away F of A, that's kind of like conditioning on C. That gives us a new submodular function, F of A given C, but it's a function of A. That's still submodular. Now here's an interesting one. There's the notion of an OR of two submodular functions. Like, suppose you have two submodular functions, f and g, and suppose you want to define essentially a set of feasible sets, A, such that you have two submodular functions, f and g, and you want the feasible sets to be that either f is greater than some coefficient, or g is greater than some coefficient, alpha g, for any non-negative coefficients alpha and g, alpha f and alpha g. So without getting into too many details, because we have a lot to cover today, this composition where and it's kind of strange because you're multiplying these two together, and you're multiplying these two together, and then you're subtracting the two sort of truncated submodular functions multiplied by each other, which ordinarily doesn't preserve submodularity. Like if you take a difference of two submodular functions, that's not submodular. But in this particular case, because you're adding this stuff and then you're subtracting the product, this, on the one hand, not only preserves submodularity, but on the other hand, it actually has the property that this new function, h, is equal to the product if and only if these two truncations are equal to the original coefficients. And so therefore, that must mean, if the new function h is equal to the product, that these original functions, f and g, must therefore correspond to feasible sets, namely greater than alpha sub f and the other one greater than alpha sub g. So you can then, therefore, when you're interested in expressing submodular constraints, do and-like constraints by summing submodular functions, and do or-like constraints by doing this particular composition. And this is a very this is very interesting. Now, probably some of you know, if you've learned a little bit about convex analysis, that there are many nice properties of composition in convex functions, and they're sort of rather succinctly expressed in this book. Now, submodular functions have similar types of compositional properties that are not the same as convex nor concave functions, but they're different, but they're equally flexible in a certain sense. So, like for example, one of the things that we can't do is like compose two submodular functions with each other. Like, with a concave function, you can take a concave function of a concave function of a variable. And the reason why you can do that is because the input and output types are the same, or at least there's possible sameness. Namely, they can be real vectors. In the case of a submodular function, the input is a set, and the output is a real number. So you can't compose, you can't take a real number and take a submodular function of that real number. But what you can do is sort of define mapping functions that map from subsets of one fundamental ground set to subsets of another fundamental ground set. And one way of doing this is with sort of like a set cover-like mapping, or sometimes what's called like a bipartite mapping. And so the idea is, again, to sort of take a ground set and break it into k, in this case, possibly overlapping subsets. And we define a new index set. So this notation here, in case you're not familiar with this, k in the square brackets basically says it's essentially the set of indices, set of integers from 1 to k. And so this is basically a function that maps from subsets of the set of indices of the set of subsets that we've got. And so now we define a new function, g, which takes indices, takes subsets of indices of these subsets, and then its valuation is the submodular function, evaluated on the union of the subsets corresponding to the indices in this argument right there. Okay. So that potentially could be a submodular function. That's a set function, right? It's a set function on one domain, namely subsets of the integers from 1 to k, defined based on another set function, namely a set function based on subsets of v. So this is the subset of v guy. This is the subset of integers of 1 to k. So then it turns out that g, this function here, is submodular if either f is monotone non-decreasing, or alternatively, if the sets are disjoint. So in other words, if it's monotone non-decreasing, the sets don't need to be disjoint. Or it could be the case that f is submodular, but the sets v themselves are disjoint. It doesn't have to be monotone non-decreasing. It has to still be submodular. That should be more clearly stated in the slide. But basically, in both cases, f needs to be submodular, but the sets themselves don't need to be disjoint. And so one way of doing this is to think of it as a bipartite neighborhood function. So we have like a bipartite graph where we have left nodes and maybe right nodes, and maybe these are the neighbors and so on and so forth. We might choose a particular subset of the left nodes, like maybe these two, and then the neighbors correspond to the whatever neighbors are on the right. And so my subset might correspond to that thing that I just highlighted in yellow, and that maps to the right-hand side, the thing that I highlighted in green, which is the thing from which we get the valuation, the subset that we get the valuation. So that preserves submodularity. So that's a form of composition, a submodular composition. Sometimes you can write it like this, like f of the neighbor's function of x. That can be very powerful, right? Because sometimes you can take very simple submodular functions and make more expressive ones. And in fact, it turns out that all monotone non-decreasing submodular functions that are integral valued, that have values in the integrals, can be expressed as one of these bipartite neighborhood functions composed with a matroid rank function. So in this sense, matroid ranks, the thing that we didn't get a chance to talk about, are very, very powerful. So here's another one that's useful, that you can compose a non-decreasing concave function with a monotone non-decreasing submodular function and preserve submodularity. Because you can take a concave function and apply it to a submodular function, and there are cases where that preserves submodularity. In fact, the well-known example of a concave function, a non-decreasing, monotone non-decreasing concave function applied to a modular function gives us a submodular function. And this theorem essentially just gives us all of those results. Like this theorem also gives us that the min of a modular function and a constant gives us a submodular function. Because a min of this function here, min of x and some constant k, that's a concave function. Right? It looks like this. Right? It goes up and it stops, and truncates. So all those sorts of things. This theorem right away gives us a lot of sort of very succinct way of recognizing submodularity. And here's sort of another, sort of maybe a slightly stronger version of this concave over modular theorem. And it says that the following two are equivalent. That if it's the case that for all modular functions, this composition, g of m of a, is a submodular function, that's true if and only if g is concave. Okay, so submodularity, therefore, and concavity have a lot in common. And since sums of submodular functions preserve submodularity, that makes this a somewhat interesting class of submodular functions. This is the class of sums of concaves over modular functions. And these are ones that the question came up yesterday about the difficulty of minimizing submodular functions. So it turns out that this class is a pretty rich and wide and widely used class, especially in machine learning. I mean, in my group, we've used this class for a lot of different applications for constrained optimization. This class in particular has a very nice set of minimization procedures that Stobbe and Krause did a couple of years ago. However, it's not the case that this captures all submodular functions. So sort of the bad news is that Vondrak showed that this class of functions can't even represent a simple matroid rank function on the graph four-clique. So matroids are powerful in that sense. Okay, so we didn't really talk about matroids, so it doesn't really make sense to talk about weighted matroid rank functions. So I'm going to skip this. But the point is that a matroid is something that gives you a very, very general class of submodular functions. And then you can take various different versions. You can modify them, like weight them slightly. And a weighted matroid rank function, as soon as you've got a weighted matroid rank function, you get all sorts of things being submodular. For example, like if you have a vector and you take the max element from a subset, let's just zoom in on this so we can look at it. So B is a subset of indices, and you take the max of the vector from the subset, that's a submodular function. And you can get that pretty readily. And so I'm going to skip over to another one that's very famous, and this is one that's used that has been used and was developed in the context of operations research. This is the facility location function. This is a function that corresponds to when, for example, there are a number of cities that are connected by a road network, and you're considering building a factory at some subset of the city locations, and you want to make sure that every city is well served by a factory, either a factory at the same location of the city or it's close to some other cities by the road networks. And you're essentially saying that every city has to be served by one factory. And so this function then gives you, in some sense, the cost of a particular choice of cities for where the factories should be built, which is a submodular function. And that was known, and that was pretty much known back in the 70s. And that's actually one of the things that motivated a lot of the work in the 70s, like the classic greedy algorithm. Yep.
So is this analogous to the set cover problem?
It's a little bit analogous, although this isn't really a set cover function, because in this particular case, you could sort of say that every city is covered by. I mean, every city is always going to be covered. And in some sense, you have some cost associated with every city and every other city, which might be indirectly through some other road network, but the costs might be high. The point is that you want, in some sense, to choose the factory to serve a city that's closest or that's cheapest to you. So it's not exactly a set cover function. But it's still one that's very, very useful. And in machine learning, it's useful because it's parameterized by essentially a matrix. So set cover, for example, you can have like weighted set cover where you have like a weight for each one of the covering subsets. So that means that you have the number of weights equal to the number of covering subsets. Here, what you have is basically, if you've got n ground elements, you have n squared weights. So the number of weights, the number of parameters is potentially much greater. But that leads to interesting potential problems for learning these things. Like if you've got a data set, how do you learn these? Someone asked yesterday, what are some important open problems in submodular functions? And I personally think, in the context of machine learning, of course, one of the big open problems is how best to learn submodular functions from data. There's only been a little bit of work on that. And I think that there's a lot of opportunity there to do, especially for you guys, because you guys are young and you guys are about to embrace the field, or actually are probably already embracing the field of machine learning. And so you have lots of years ahead of you to work on this. So we said before that, submodularity actually captures notions like information. So the entropy function, so this is what we mean by the entropy function. The entropy function seen as a function of the subset of random variables. So this is really important. So the idea is that you have some large joint probability distribution, and you take the entropy of a subset of that random variable. So it's not a continuous function. It's still a function of subsets, but the subsets are basically a choice of random variables. And so entropy is the submodular function. In fact, it's a monotone non-decreasing submodular function. Okay. And the reason why it's submodular is basically an immediate consequence of a very fundamental inequality in information theory, and that's basically the Shannon condition for the non-negativity of the conditional mutual information. So this is something that Claude Shannon outlined back in the 1940s for entropy, and he argued that that was a very natural condition for any function that should be seen as an information function. So little did he know, or maybe he did know, but maybe he didn't know. Either he did or he didn't. Definitely one of those two. Maybe there's a third option, but not in this universe. So, but little did he know that he was actually defining submodularity in his 1948 paper, although very, very disguised, and in the context of it. So what I think this is testament to is that all of his arguments for why entropy is a useful information function also apply to polymatroid functions, because the same inequality holds. We saw this last time. These are all of the sort of generalized submodular dependence notions. But there's also the continuous entropy, or what's sometimes called the differential entropy. And the differential entropy is where instead of a sum, you have an integral. And if it's a Gaussian, if f is a density function, it's a Gaussian density function, then it turns out that the conditional entropy, the continuous entropy, is basically has this form, which you can write as a modular function plus a log determinant of a positive definite matrix. And so now you've got a function of a subset which is a log determinant of a submatrix of some positive definite matrix. And that basically, since entropy is submodular, we immediately get the submodularity of the log determinant function. Now there's a hard way of proving that. In fact, there are folks in the 1990s who have like 3 or 4 page proofs of this fact. But we get it for free thanks to the submodularity of the entropy function. So here's a really interesting and deep question, which is information theoretically relevant. And the question is, are all polymatroid functions entropy functions? Because entropy, in some sense, is very, very general. I mean, entropy, also lives in a cone of dimension 2 to the n, and there's all sorts of stuff you can do with entropy, especially when you consider the diversity of different random variables, and you're not even like talking about the cardinality of the random variables in the discrete case, or you're not talking about anything associated with the the continuous random variables that you would be doing if you were to compute differential entropy. So the question was open for a while, and it turned out that, interestingly enough, that entropy is a smaller set of functions than the submodular functions are. And it's shown by saying that if you are an entropy function, Jung showed this in 1998, that if you're an entropy function, that the corresponding mutual information function must satisfy these inequalities. These are called non-Shannon inequalities. The reason they're called non-Shannon is because they're not directly apparent. They're not directly implied by the Shannon inequalities that were defined in the 1940s, which correspond to the submodular inequalities. These are ones that don't directly follow, yet must be true for any entropy function. So therefore, entropy is a strictly smaller set of functions. So another open problem is coming up with better characterizations for the difference between the submodular functions and the entropy functions. Like what lies within that space that is really different about the entropy functions? What can you do there? People are beginning to characterize it, but I think it's still not yet fully understood. So then the taxonomy in some sense is that submodular functions are strictly greater than polymatroid functions, which are strictly greater than entropy functions, which are strictly greater than Gaussian entropy functions, which basically, since it's a log determinant, corresponds to determinantal point processes. Okay, and we saw determinantal point processes before. Already, determinantal point processes are extraordinarily useful in machine learning. And I should mention that another reason why determinantal point processes, I mean, it's not necessarily always the case that generalization is better, right? Because abstraction, you could just abstract all the way up to it's a thing, right? You'll say, well, I've got this thing called a thing, and that abstracts everything. That's not necessarily useful. I'm claiming that submodularity is a useful abstraction, but there's also utility and specificity as well. And so, for example, in this case, in the determinantal point processes case, you can bring to the table an enormous array of matrix tricks that you can use to do efficient computations with determinantal point processes. And so that's one of the additional advantages of DPPs. There's so much known about matrices. Okay, so I'm going to talk next about semi-gradients, and in particular discrete semi-modular semi-gradients. So first of all, in the case of convex functions, whenever you have a convex function, you have a derivative at a point. And what's shown here is like the blue guy is a convex function and the red guy is a derivative at b. And more generally, it's called a subgradient. And the reason why it's subgradient is because you can have a convex function that maybe looks like this. It's a polyhedral convex function. And there can be multiple subgradients. It can be this one or this one and this one. Those are all subgradients that are tight at this particular point, right? When it's continuous differentiable, then there's going to be one subdifferentiable, which is the subgradient. And one way of describing it is essentially, the equation that describes a subgradient is this. It's equation 107. So that whenever f is convex, when the function f is convex, the subgradient is an affine function. It's a linear function plus an offset. And it's tight, right? It's tight at any particular point. And convex functions have, whether it's a differentiable or non-differentiable convex functions have tight subgradients at every point in their domain. Concave functions have supergradients. So now we've got a concave function, and supergradient is sort of just the mirror image of a subgradient, right? So it's tight at any point. It doesn't matter if it's differentiable or not, but it's an affine function that's an upper bound everywhere. In the case of a subgradient, it's a lower bound everywhere that's tight at any point. In the case of a supergradient, it's a affine upper bound that's tight at any point that you want. Right? So it's tight at one particular point. In this case, it's tight at B. Okay. Now the question is, we have this sort of notion of affineness in the discrete world, which is the modular functions or the additive functions. Sometimes, in fact, they're called linear functions. And so we can actually get trivial upper and lower bounds for a submodular function. So here's a submodular function evaluated at A, and we can get a modular upper bound by just basically summing the singleton elements. That's a guaranteed upper bound for any submodular function. And we can get a guaranteed lower bound by summing the smallest possible gains of A. Because remember, the f of A given V except for A. So that's the smallest possible value that A can be. And do you remember what that is? That's basically, in case you don't remember, that's this thing here is equal to f of V minus f of V except for A. So that's like the gain you get in adding V to the largest possible context, which is everything except for A. And then creating a modular function based on those guys gives you a lower bound. Okay, but these are upper bounds and lower bounds that are additive, but they're not necessarily tight at any point. Like in the case of a concave function or a convex function, in a convex function, we can essentially take this affine lower bound so it's touching it anywhere we want it to be. In the case of a concave function, we can take this affine upper bound that's touching, that's everywhere above and touching wherever we want it to be. This is not necessarily touching anywhere. Now, submodular functions turn out to have subgradients in the same sense as convex functions have subgradients. And they're defined in the following way. They're defined, in fact, exactly analogously, or exactly identically in some sense, to the way that subgradients of convex functions are defined. And so therefore, it seems, and it's been long known or thought, that submodular functions are therefore very much like convex functions because they have these subgradients that are tight everywhere, or subgradients that can be tight anywhere. And in fact, you can partition, since we know that modular functions are basically points in Rn, you can partition Rn into these regions of subgradients. So like here's the subgradients evaluated at the empty set, and here's the subgradients that it's evaluated at the ground set, which in this case is just a ground set of size 2. So this is R2, but in general in Rn, it partitions Rn into these regions of these blocks of subgradients. Okay. And moreover, the extreme points, as we will soon see, are very easy to get. So these are really interesting points because these points in red that I just marked correspond to things that delineate where the boundaries of the subgradients are. And thanks to Edmonds' greedy algorithm, which we're going to talk about in a minute, we get them. Actually, did we? Wait a second. Yeah, I think we actually need to go back to define Edmonds' greedy algorithm. It turns out that any extreme point can be represented by a maximal chain. Like you take a maximal chain, and then you construct a vector that has elements equaling to the evaluation of the difference on that chain. Basically, it's like if you take a chain which is S0, S1, S2. So what is a chain? A chain is basically a sequence of sets. The next one has got one more element of it than the previous one. And we take the difference of the submodular function evaluated on two successive elements in the chain, and then that gives you the coefficient. That gives you the coefficient for that new element in the modular function. That gives you an extreme point of the subdifferential. I want to formally define a polymatroid function. So a polymatroid function is a real-valued function f that is normalized in this sense. Okay, it's monotone, non-decreasing. So that basically means that as we keep adding stuff to the set, the valuation of the function cannot decrease, and it's submodular. So, like I was showing before, all polymatroid functions are submodular, but not all submodular functions are polymatroids. But as we talked about yesterday, any submodular function can be represented as a sum of a polymatroid function, one that has these properties, and a modular function. Now, what's interesting about polymatroid functions is that they have all submodular functions have a polytope associated with them, a polyhedron. The polymatroid functions have a polymatroidal polytope, which is defined in the following fashion. So there's the name of it. And it's all vectors in RV, so in the positive orthant, or the non-negative orthant, such that this set of linear inequalities is satisfied for all subsets. So how many inequalities are there? There's an exponential number, right? There's 2 to the n. Because for all possible subsets, we've got an inequality. And the inequality is basically based on summing up the elements of the vector corresponding to A, and it's also based on the valuation corresponding to the submodular function. Now this, of course, isn't in general guaranteed to exist, even. If you take the intersection of incompatible half spaces, that might be the empty set. In the case of a polymatroid function, you're guaranteed that this exists on the one hand, but you're guaranteed that it has a bunch of interesting properties as well, as we'll soon see. So first of all, I should have mentioned this before. So what do I mean by chain of sets? So a chain is where you have a particular ground set, and you have a permutation of the elements in this ground set. So sigma is a permutation. It's just any arbitrary permutation that you want. And then you form a chain of sets, which is a sequence of sets that have a subset-superset relationship with respect to each other. So basically, given this permutation, so here are the elements in this permutation, okay? And here's the first one, which is C1. The second one, which is C2, is the first 2. The third one is the first 3, and so on and so forth. So this gives you a successive chain. And so Ci is basically the first I elements according to the permutation. And you can form permutations based on a number of criterion. Like, for example, if you have a vector W, you can sort it in decreasing order. And then you choose the permutation to be one that vector is sorted in decreasing order. And that's a really important thing, because that's actually, it turns out, going to be the thing that defines the Laplace extension as well. So hopefully this concept of a chain and creating a chain based on a sorted order of a given vector can be something that you can quickly internalize. The other thing I wanted to mention is this notion of gain. So there's lots of notations. If you go read the literature, and I hope that you do start reading some of the literature, but you will see gain. This notion of gain is sort of so fundamental that it occurs in lots of different ways. So sometimes you'll see it written as rho sub j(a). Sometimes you'll see it written as rho sub a of j. Sometimes you'll see it written as a gradient-like thing, and sometimes you'll see it written as this conditional form. There's arguments for all of these. The only thing that's difficult is it gets confusing, in particular these ones, which completely reverse the argument. But you'll see them in all these different forms. And the one that I like to use personally is this one, because it's inspired from information theory. In fact, there are some people in the information theory community who've done a little bit of work on submodularity, or I should say a lot of work on submodularity, and they actually use this notation. So with this notation, with this gain notation, the definition of submodular becomes trivial. It basically says that f of j given a is greater than f of j given b whenever b is bigger than a. Right? So conditioning reduces valuation, just like the entropy. So it's the same definition. Now consider the following linear programming problem. So we want to maximize. We have some vector w. And we want to maximize the dot product of w times x, where x is a real vector, subject to x being in this polytope. This is the polymatroidal polytope. Okay. So essentially, we can sort of, in short, write it in this fashion. So in general, if you're faced with a linear programming problem that has an exponential number of constraints, would you generally tend to think that that's easy? Would you go and take your favorite linear programming problem, list all exponential number of constraints, and then just read it as a file? Especially, what if the number of variables was 100 and you had 2 to the 100 constraints? That would be a little bit hard, especially if each constraint is important. In other words, if there's no redundant constraints. So this problem, you might think at the outset, is impossible. It's impossible to solve, impossible to scale. But it turns out that the greedy algorithm solves this exactly for this particular case, if the function that defines the polytope here is a polymatroid. Okay. So what is the greedy solution? Well, the greedy solution basically says the following. We sort the elements. We take the vector w, so w is like an input parameter, and we sort them in decreasing order. Okay, and that gives us a permutation. And let's, without loss of generality, just assume that that V is ordered or is renamed in the order of in the decreasing order of the vector W. Okay. And so we define a chain. So Vi is the first I elements according to that order. And then we define a vector based on this thing that I said before, where the ith element of the vector basically gets valuation based on the difference between of the submodular valuations on successive elements in that chain. Or in other words, it's just the conditional submodularities. It's the f of Vi given everything that came before it in the ordering. So it's order n valuations of the submodular function. Okay. So it turns out that there's this extraordinarily amazing, powerful theorem that was proven by Jack Edmonds. And it says that, let's say that f is a given set function, and p is a polytope of this form. Okay, so the green bit is like, we're not saying anything about submodularity yet. Okay, we're saying here we've got this set function, we don't know anything about it, and we define this polytope defined by it. We don't even know if it exists. But what the theorem states is that the greedy solution, the thing that we just outlined, for this exponentially large linear programming problem is optimal for all W if and only if the function f is monotone non-decreasing submodular, namely, or in other words, if f is a polymatroid function. So greedy and polymatroidality, or greedy and submodularity, in some sense go hand in hand. The notion of greediness from the perspective of solving these linear programming problems is identical to the notion of polymatroidality. Yep.
But you still have to be able to sort the set, right?
You need to be able to sort the vector. Yes. You need to sort the vector, and that takes n log n time. So you still need to be able to sort. And then you need to be able to evaluate. But that's very different than, say, the exponential number of constraints. I mean, it's amazing because in general, like when you think about submodular function minimization, here you've got something which has 2 to the v degrees of freedom, right? But you're minimizing it, even though if it is in the worst case n to the 6th. So what? You've got something with exponential number of possible values, an exponential number of degrees of freedom. And when you're doing submodular minimization, you get the exact solution in polynomial time. So that basically means that you're ignoring an exponential number of possible values, so that you could wiggle an exponential number of values in this space of 2 to the n dimensional space, and you haven't changed the solution. So that's a remarkable thing about submodularity. And here also is something remarkable, where somehow you must somehow be capable of ignoring a very, very large number, an exponentially large number of the set of constraints, yet you still get the exact solution. So submodularity really sort of gives you powerful implications. So first of all, let's talk a little bit about what these polytopes look like. So here's the submodular polytope, the polymatroidal polytope in 2 dimensions. And so this is a nice picture because it gives you a sense as to why greedy works. The axes are labeled based on the valuations of the submodular function. So this length is just f of E1, and this length is f of E2 given E1. And this is, now let's compare this length here with this length here. Notice the one on the right is f of E2 given E1, and the one on the left is f of E2. Conditioning reduces evaluation. So when we condition on E2, it's got to get shorter. So therefore, we have that this guy is shorter than that one. Right? That's what guaranteed from the submodularity property. And then similarly, we have that this one is shorter than this one, which is also guaranteed from the submodularity property. But then we also have, from the definitions of these things, that this is going to be guaranteed to be a negative 45 degree line. This, by the way, is called the base of the polymatroidal polytope. Okay. So now why does greedy work intuitively? So let's say that you're a vector. Have you ever had that feeling? You wake up in the morning, you say, I'm a vector. And then the other person next to you says, no, I'm a matrix. And then you get into an argument. And then you go have coffee. And then you say, what were we talking about? And so let's say that you're a vector. Okay? And let's say that's the you. So that means that you're slightly larger in the E2 dimension than in the E1 dimension. And so greedy basically says, okay, so this is W. Right? Here's W here. And so you want to maximize, you want to find the maximal direction. So what greedy says is to first go this direction and go this direction, and it will say that that's the best x, right there. Now, why would that be the best x? Well, anything that is to the left of this green dot is going to, so it's basically you're taking the dot product of that green dot with W. Okay, so anything as you move to the left of that green dot, you're going to be decreasing the dot product value, right? Because the height is the same, but the farness to the right is going to be shrinking. What about when you go this direction and when you go down along this face? That's also going to be shrinking the dot product. Because why? Because you're higher because your coefficient in this dimension is bigger than your coefficient in this dimension. And so if you go down this way, while you are moving to the right as fast as you're moving down, when you actually consider the dot product, you're actually shrinking your objective, which is W times x. So therefore, the greedy algorithm gives you the optimal solution. And moreover, the greedy algorithm gives you a point, an extreme point of the polytope. Okay? So that's the intuition. That's why it works. I mean, just pictorially. You can actually look at a three-dimensional polytope. And you can see that all these faces look kind of the same. Let's zoom in a little bit on one of them. You see that guy? So he kind of looks like a two-dimensional thing of what we just saw. Right? So why is he two-dimensional? Because, well, here's the valuation of f of E1 given E2. And here's f of E1 given E2 and E3. Conditioning reduces valuation. So this valuation up here is going to be less than this valuation. Right? And so we shrink. This is going to be 45 degrees again. But then, every single one of these is going to be the same thing. And then this face over here, this guy, is going to be essentially just the 2D hyperplanal version of the base. And this is called the base polytope. This is also a polytope here. It's called the base. And that's a very important thing for minimization problems, which I will touch on in a little while, in the next 35 minutes. Okay, so that gives you, I think, this picture and this picture, I think, hopefully will give you a nice intuitive sense of what the polymatroidal polytope is. And I'd just like to say that this was all done essentially by Jack Edmonds, this guy right here, who I should mention he gave a talk at our Discrete Optimization and Machine Learning workshop a couple of years ago at NIPS. And so you can go to videolectures.net and actually see the guy himself. He's still alive and he's still lucid and talking about stuff. So that was not meant to be anything. He's a really amazing. He's still very, very sharp. I mean, he's incredible. All right, so now we're going to move back to where we were. So we were talking about these subdifferentials, and you can start seeing now that the subdifferentials, the subdifferential at 0, which is this one, corresponds to a shifted version of the polymatroidal polytope. And it's shifted based on a modular function. In fact, that's the submodular polyhedron. It's no longer necessarily entirely living in the positive orthants, but the subdifferentials in general correspond to essentially a partition, one of which, the one evaluated in the empty set, is exactly the same as the submodular polyhedron. And you get that by and this is what happens when you give a tutorial at the end of your cold, is you lose your voice. I don't feel as bad as I sound. So, any questions? How's that? This is a good time for you to talk. Okay, so we can essentially get subgradients very, very easily by running the greedy algorithm. The greedy algorithm, if we take any order we want of the elements, that will give us a subgradient by defining the modular elements to be equal to the difference of the successive valuations of the submodular function according to that order. And we can get tight subgradients at any point by ensuring that we choose an order. Let's say that we're interested in a subgradient that's tight at value, say, y. Okay, so let's say that y has 15 elements. So the size of y is 15. So it's a set of size 15. So you choose any order that you want as long as when you take the first 15 elements in that order, that exactly equals to y. And so what that does is it gives you an exponential number of subgradients, all of which are tight at that value y. And that's essentially what this is saying. So basically it's saying it's really easy to get subgradients from a submodular function. Now here's something that's also, I think, absolutely remarkable. Let's take recourse for the moment in the continuous world and think about the notion of whether there's a possibility of there being tight both sub and supergradients at any point for a continuous function. So what does this mean? So let's say that we've got a supergradient of a function that's tight at this point here. So that all that means is that this green line is an upper bound of the function, and that at this point it's exactly equal to the function. And now what we want to do is have a subgradient that's tight at that function. That's a lower bound of the function that's tight, again, at that very same point. So what does that leave you between? There's only one function that can live within those two functions, and that's an affine function. So basically it's saying that any function in the continuous world that has both a tight sub and supergradient at any point must be an affine function. Right? But must that be also true of discrete functions? So it turns out, strangely enough, that thanks to the following set of inequalities, and we don't have time to get into these inequalities. These look a little bit hairy, but it turns out that these are additional inequalities that actually are defining for submodularity. In other words, if these inequalities are true, then you've got a submodular function. So we relax these functions a little bit, and what this gives us is natural and very easy to obtain supergradients of any submodular function that is tight at any point. So what that means is that if you're a submodular function, you can get an exponential number of subgradients that's tight at any point, and you can get these supergradients that's tight at this point. And these are things that are easy to get. These are all basically, the subgradients are basically choose an order, right? So it's just linear time. These ones are also easy to get. Okay. So this is very, very important for discrete optimization. So here's another area which I think is an open area for research for submodular functions. So everybody probably is familiar from being here for a week that first order gradient-based methods are very, very important for machine learning these days. And the reason why is because they at least intuitively, I mean, you've probably heard this in the deep modeling session, that in terms of the amount of optimization you get per floating point operation on a computer is very high for a first order method. Right? If you take a second order method or much more complicated methods for optimization, maybe in terms of the total number of iterations you do might be a little bit shorter, but in terms of the total number of computational fundamental operations you do, first order methods are very, very efficient. Now for discrete optimization, first order methods hasn't traditionally been as viable, mainly because subgradients haven't been as readily attainable, in particular subgradients and supergradients. But what this is saying here is that if you have a submodular function, and let's say you have some particular submodular optimization problem, that both subgradients, tight subgradients and tight supergradients are available. And so maybe this means that some of the benefit that exists in the first order world for continuous optimization might be, borrowable in the discrete world. At least that may be true. And some of it is beginning to be true based on some of the research that we've been doing. Okay, so let's talk a little bit about the Lavache extension, because that's an important construct, very, very briefly. So if you have a discrete function, you can always take any discrete function and extend it to a continuous function, right, by just interpolating. And so here's a bunch of discrete functions. And in fact, here are, on the left-hand side, the discrete function is basically evaluated. It's a simple function that has two values based on 0 or 1. And you can extend it in this concave way, or you can extend it in this convex way. And there's lots of different concave and convex extensions. In fact, there's an unbounded number of them. And the question is, how do we get useful ones? And like one thing we might be interested in is the convex envelope. Like in the case of a convex extension, we're interested in the largest convex function that agrees with the points that you've got in the discrete world. So an important question regarding such extension is, when are they computationally feasible to get or to estimate? Like, because the convex envelope or the concave envelope may not be easy to get in general for a function, for a discrete function. It might be exponentially hard to get it. And secondly, when do they have nice mathematical properties? When are they themselves useful for something? Like, for example, if you do a convex relaxation, is there going to be an integrality gap? Right? And maybe most importantly, when are they useful for something practical? So the Lavache extension is a continuous extension that has all of the nice properties when it's a submodular function. So here's what we've got. So basically, we've got a submodular function f and a w, and we define a chain, the same thing where we sort w in decreasing order, and then we choose that particular order, and we define w based on the following operation. First of all, it's equal to this linear programming problem, which we said is solvable by the greedy procedure, right? So now what we're doing is we're turning the linear programming problem into an evaluation. We're turning it into evaluation or a function of w, which is the vector. And so since it's solvable by the greedy algorithm, we have an expression for this function. It's basically the sum of the weighted conditional function evaluations, but where we have to make sure that we've ordered the elements in this decreasing order according to w. And here's just the same thing written out a little bit more explicitly in terms of the difference. And then we can regroup items so that now we've got essentially a set of coefficients that weight individual function evaluations. So it's seen now as just a weighted combination of the submodular functions. Okay, so we've got this weight, and then we've got a bunch of weights here which correspond to a difference of the w's. And so therefore, the continuous extension can be written in the following fashion, where we just basically take a sum of weighted function evaluations, where the function evaluations are on the chain of sets defined by the ordering given by sorting w in decreasing order. And so here's the definition of the coefficients. You saw that in the last slide. Now, since it's the case that we've defined the function in this fashion, from convex analysis, we immediately know that this is a convex function, right? There's a maximum over a bunch of linear functionals. And that's always going to be convex. And that's even true when f is not a submodular function, right? So any particular set here, it doesn't even need pf, doesn't even need to be convex. You just take a bunch of max over a bunch of linear functions. However, we can just define an extension in this way, like it's the sum of weighted coefficients, where we've just defined the weights in this fashion. So we define the chain according to sorting the w in decreasing order, and we just define it in this way. So whether or not f is submodular, we just define an extension, a continuous extension of a function in this fashion. Okay. And it turns out also that just by the way we've defined these coefficients, that W itself can be recovered by the coefficients by taking a sum of weighted characteristic vectors of the corresponding sets that we're also using to evaluate the submodular function on. Okay? So that actually defines the Laplace extension. And the reason why it's called the Laplace extension is because Laplace showed that any function, any discrete function that's extended in this particular way is convex if and only if the function is submodular. And it actually ends up being, moreover, the convex envelope. So it turns out that submodularity and convexity are related to each other in this fashion, that the convex envelope is easy to get via the greedy algorithm, and moreover, this particular expression of the function, where we've defined the coefficient lambda in that way, based on the differences of the w's when they're sorted in decreasing order, that's going to be convex. So does that mean that submodular functions are just like convex functions? No, because we could take a concave function of the submodular function as well. Concave extension or concave. In fact, there's lots of convex extensions. There's lots of concave extensions. It just means that this particular convex extension happens to be very, very easy to get when the function is submodular, but not when it's not submodular. So submodularity enables the acquisition of the extension very easily. But there's even more power to this because the extension, it's a continuous extension that has an integrality gap of 1. And that's shown by saying if we take the minimum of the submodular function over all subsets, that's basically equal to the minimum of the Laplace extension evaluated on all vertices of the hypercube, which is equal to the minimum of the Laplace extension evaluated anywhere in the interior of the hypercube. So therefore, we can turn submodular function minimization into this convex minimization problem. And this theorem was the first critical step that allowed people to prove the polynomial time solvability of submodular function minimization back in the very late 70s, based on the ellipsoidal algorithm and using a separation oracle, using this essentially as a separation oracle. So I'm going to skip this part. But are there any questions about this theorem or Laplace extension? Yeah.
I couldn't understand the equality, like from the integer to continuous. Yeah, this one.
Sorry, say again.
So
I couldn't hear the question. I'm sorry.
The equality where you
the equality?
Yeah, the W from the 0, 1 to the continuous space.
So there's two equalities. So there's this one, this yellow one, and then this green one. Which one you want to do? Second one. Okay. So the only difference here is that in one case we're optimizing W on the vertices of the hypercube. So here's a hypercube, right? So in one case, we're basically just optimizing on these vertices. We're just evaluating on each one of these vertices and finding the minimum. In the second case, on the right, we're looking everywhere on the compact interior, or the closed interior, I guess is a better way to say it. And why are they equivalent? Well, we have to prove that. We would have to prove that. So they're equivalent because, I mean, you can show, you show it by convex duality, turns out. So I should mention, actually, that we don't have time in this tutorial to go through any of the proofs, but I teach a class on submodular functions and optimization, and I happen to be teaching it now, and all of my lectures I'm putting them on YouTube. So if you want, you can go to my class page and watch the lectures, and in class we actually go through all of the proofs, including the proof of this theorem. And we go through it in enough detail that you can just watch it. So feel free to go to YouTube and have the full proofs of every single theorem that we've mentioned, and including many other theorems that we haven't mentioned are proven in this class. So if you're interested in that. It's just I want to move forward because we only have a little bit of time left. But one thing that's very interesting, however, is that when we can use the Lavoisier extension to sort of show, I mean, we can minimize the submodular function based on just minimizing the Lavoisier extension. And then once we have a solution, what this set of equations shows you is that it's very, very easy. Like you might get a continuous solution, and usually when you do an extension, a continuous extension of some sort, you have to round the solution. And if there's an integrality gap, there's a potential you're going to get some approximation error. In the Lavoisier extension, there's no integrality gap, but you still have this issue of you've got a continuous solution and you need to somehow get back a discrete solution. And it turns out from that continuous solution, it's very, very easy to get not only a discrete solution, but a whole slew of equivalently discrete solutions, small ones and big ones, that have the same valuation. Or if there's only one, then you only get one. And that basically, again, comes from sorting the vector and then choosing sets according to the sorted order. Moreover, this actually gives us, through convex duality, something called the minimum norm point algorithm. So the minimum norm point algorithm was essentially an optimization algorithm based on the Frank-Wolf procedure to optimize this objective here. And it's been long known that the minimum norm point algorithm is, people don't know the actual complexity. Unlike linear programming, this is an algorithm whose complexity is unknown. But in practice, it seems to work very well for a wide variety of general purpose submodular function minimization purposes. But it turns out that this is actually dual to this sort of regularized Lavoisier extension minimization problem. And so that's one way, and there's strong duality here. So you get the same solution. Okay, so I don't have time to go into a lot of that. So let me just sort of outline where the Lavoisier extension is useful. So it's useful for fast submodular function minimization. We saw yesterday that Lavoisier extension is useful for structured convex norms. It's also, interestingly enough, useful for nonlinear measures and nonlinear measure theory, which is something that's not seen the connection to machine learning in a while. And it's also useful in game theory. In fact, the Lavoisier extension was originally proposed by Choquet in 1954, and it's called the Choquet integral. And it was even sort of proposed a little bit earlier, or at least a form of it by Vitali in 1925. So these things go way back, and they sort of continue to be rediscovered. So there seems to be something fundamental in this particular extension, because it's been rediscovered in a number of different contexts. I do want to mention that there is a concave extension to submodular functions, but in general, finding the concave envelope is NP hard. But you can get a concave-like extension called the multilinear extension. And it's not concave, nor is it convex, but it's concave in certain directions. And with this, you can actually optimize using continuous greedy-like algorithms and get boundedly good solutions for a variety of submodular function maximization problems subject to various constraints like matroid constraints and knapsack constraints. So while if you have this, it's nice because you could just treat it as an oracle. But in practice, it's a little bit tricky because notice that the multilinear extension itself requires an exponential number of terms in the sum. So just unlike the Lavoisier extension, the multilinear extension is not so easy to use in practice. So oftentimes what people do is they'll do MCMC, and they'll sample, and they'll try to come up with good estimates of this based on sampling procedures. So everything you learned this morning is important for what we're talking about. So what I wanted to talk a little bit about was something that comes up a lot is, are submodular functions more like concave functions or more like convex functions? So I thought that maybe we'll do a little bit of comparison. So they're like convex functions because submodular functions can be minimized efficiently. or in polynomial time. They're also like convex functions because the Laplace extension is convex if and only if the function is submodular. There's also a separation theorem. There's Frank's discrete separation theorem that says the following. It says that if f is a submodular function and g is a supermodular function, and you have this inequality, that g is always lower than or equal to f, then there exists a sandwich-like procedure. There's a modular function that lives in between the two. And so this is very, very much like what happens in the convex and concave case. So which function is taking the role of the submodular function? Well, f is the convex function. So there's a separation theorem in convex analysis, and there's a separation theorem in submodular analysis. So submodular functions are also like, so it's like convex. So the topic came up of, yesterday someone asked about convex sets. So in continuous analysis, you can talk about a convex set such that if you take any convex combination of points, anything in between is going to be in the set. And then if you take a convex function and you minimize it, if you have multiple minimizers, that set of minimizers are going to correspond to a convex set. So there is no notion of a convex set in submodular analysis, but there are things like lattices that I mentioned. And it turns out that all of the minimizers of a submodular function comprise a lattice. And so what that means is that if you take any two minimizers, and there can be, there doesn't need to be more than one, but oftentimes there is more than one minimizer. So if you take any two minimizers of a submodular function, then the union of those two is also a minimizer, and the intersection of those two is also a minimizer. So minimizers are closed under union and intersection. So that essentially gives you a Boolean lattice of minimizers of a submodular function. And also, like convex functions, submodular functions have subdifferentials that are tight at any point. OK, so next, why is submodular functions like concave? So now the title is actually correct up here, concave. So they're like concave because, one of the definitions of submodularity is actually this. It's kind of like a special case of what we saw, but it turns out that that's sufficient to define submodularity. So f of x plus j plus f of x plus k is greater than or equal to f of the union plus f of the intersection. So that already defines submodularity. It's one of those properties that defines it. So if we reorganize this and we use the derivative notation for the gain, it turns out that that condition up here, equation 229, is identical to negativity of a form of second derivative. So what functions have the property that if they're negative, if their second derivative is everywhere negative, what functions have that property? Concave functions. And so therefore, when you take the derivative form of these discrete functions, the second discrete derivative is always negative. So therefore, submodular functions are like concave in this way. So secondly, we had theorem 16, which said that if we compose a concave function with another submodular function, which could be a modular function, you're going to get a submodular function. So therefore, concave submodular functions have this diminishing returns thing. I mean, when we plot submodularity, we often sort of think of it like that. Like the more you have, the less valuable anything you don't have becomes. So they're very concave-like. In fact, that is sort of a defining property of concavity. So also like concave functions, submodular functions have tight superdifferentials and supergradients at any point. I also like concave functions. Maximization, you can't solve submodular maximization exactly. It's NP hard to solve it exactly, but you can approximate it pretty well. The greedy algorithm gives you a 1 minus 1 over e approximation, which I'll talk about in a few minutes. But on the other hand, submodular functions are also neither like concave nor convex. So submodular functions have simultaneous sub and supergradients. Convex functions and concave functions don't have that. So concave functions are closed under min. Submodular functions are not. Convex functions are closed under max. Like if you take them, just to make sure this is clear, if you take the max of two convex functions, you still got a convex functions. That's not true of submodular functions. Convex functions can't, in general, be approximately maximized, but submodular functions can. So convex maximization is hard. Convex functions also have local optimality guarantees. Like, there are various forms of optimality guarantees for convex functions, like the following. Like, if this is true and it's an unconstrained convex maximization problem or minimization problem, that's a guarantee that you've got a global optimum. So there's no simple sort of local optimality that guarantees global optimality for submodular functions. There are things which I'm not mentioning here where a form of local optimality gives you maybe a greater range of local optimality, but not global optimality like you get in the concave, like you get in the convex case. Okay, so the last topic I want to talk about a little bit is optimization. So, basically we've got submodular maximization and minimization and unconstrained versus constrained. So let's start off with maximization unconstrained. So in general, like if you have a polymatroid function, it's trivial to maximize. You just take the ground set, right? Because it's ever growing. Anytime you have a monotone non-decreasing function, it's easy to maximize. So the only case, in some sense, it doesn't really make sense to even talk about unconstrained polymatroidal maximization. But here, if it's a polymatroid function, you really have to talk about like some sort of constraint, like maybe a cardinality constraint. And so maybe what should really be done here is that you should talk about monotone versus non-monotone. Okay, so the greedy algorithm guarantees in the monotone cardinality constraint case to give you a 1 minus 1 over e guarantee. In the non-monotone case, a form of greedy, like a bidirectional greedy algorithm, gives you a 1/2 guarantee, which is the best you can do, unless p is equal to np. Okay. So that's the unconstrained case, or the semi-unconstrained case. In the constrained case, like if you've got maximization subject to matroid constraints or multiple matroid constraints, in general, these become NP hard. But oftentimes it's approximable with still, again, the greedy algorithm. Like, for example, with a matroid constraint, or if you have multiple matroid constraints, the approximation guarantee becomes like 1 over the number of matroid constraints that you've got. Which, if you want, in some sense, sort of a quick and dirty solution for a matroid constraint problem, that's actually not, that's actually maybe reasonable, because the greedy algorithm is so efficient. But there's something called the curvature, which I do want to define very briefly. The curvature is something that makes things a lot nicer. So there's a notion of a curvature of a submodular function, and if the function is not too curved, the guarantees get much better. Okay, so next, we've got unconstrained minimization. So that's polynomial time, although it's hard. But there are many special cases. Graph cut is one. Sums of concave over modular is another one. Piecewise linear approximations of concave functions, sometimes those can be optimized exactly in lower polynomial time. So there's a number of instances that can be done lower to polynomial time solvable. And this is an open research area. That's how do you improve this? Because nobody knows what the lower bound is in general. I asked one of the founding fathers of submodularity, Satoru Furushige, what he thought the lower bound was. And he told me, he said, I hope it's n cubed, but I think it's n to the 4th. So that's what he said. So, but we don't know. We don't know. So, and then lastly, we've got constrained minimization. That in general is hard even to approximate. But many problems it's still approximable. In particular, if you start talking about curvature dependence, like as soon as curvature becomes into the picture, if the function's not too curved, you do get a guarantee, as I will talk about. So here's sort of an outline of the history of submodular function minimization. Interestingly enough, it sort of all starts from Jack Edmonds' work. It's his seminal work back in the 1960s. And that led here to the first polynomial time solution to submodular function minimization. And that also started this whole flurry of work on combinatorial or non-continuous methods for submodular function optimization. These methods are very, very tricky and complicated. These are the ones that have these very, very high complexities. In fact, I don't think there's ever been instances, many of these methods aren't even implemented. So you know they're theoretical worst case complexities, but because they're so complicated, nobody's really coded them up. What has been coded up is Frank Wolf's and Fujishiki's version of the min-norm algorithm, which is what I've mentioned to you. And so that was coming from this direction. That's the minimum norm point algorithm. And then very, very recently, Bach basically looked at the smooth, sort of like the Prox regularized Laplace extension and tried a number of different convex minimization procedures in the primal, because the min-norm is kind of a dual optimization version. The convex Laplace extension minimization is a primal. And his results found is that there doesn't seem to be any clear winner. A lot of it depends on how much engineering effort you put into the convex minimization procedure. And sometimes one wins, sometimes the other wins, but min-norm is basically still pretty much a good general purpose submodular function minimization procedure. And there are implementations of this. In fact, my lab is working on a fast C++ one right now that hopefully we'll release at some point. There's constrained submodular minimization. And so the constraints might be things like cuts or paths or matchings or cardinality constraints. So for example, do you remember the graph cut, the cooperative cut example I gave yesterday showing the elongated structures and the shrinking bias problem and the contrast gradient problem? That corresponds to a submodular function minimization problem constrained to a cut. Right? And there are there are actually bounded approximations for these. So in general, when you want to do a minimization problem, you want to say something like this. Like f is the solution that you get is no worse than alpha times the best possible solution for some alpha greater than 1. And the kinds of alphas that you get for these kinds of problems are not constant. So they're not constant factor approximable. So for example, like cuts, you get square root of m, where m is the number of edges in the graph. And you have all of these other essentially approximation guarantees. These are, the lower bound is the worst case. So that basically means that you can never do better than this. And these are various different strategies for it. So we're pretty much tight. In other words, pretty much that's all there is to be said for both upper and lower bounds. Okay. Other kinds of constraints are easy, like certain types of lattice constraints, or even and odd set kinds of constraints. You know, so in some sense, like lattices are like the discrete analog to convex sets. And so you can do submodular functions constrained to certain types of lattices, and that's still polynomial time, interestingly enough, even though lattices can be very flexible. So for submodular maximization, it's basically just the greedy algorithm. The greedy algorithm is extraordinarily simple. You start with the empty set, and then you keep adding next whatever looks best at the time. So you just keep adding elements to the set, the elements, whatever is the one that increases the valuation the most. And you keep doing that until you're no longer feasible. For example, like you're no longer of size k, or you're no longer an independent set in a matroid. And in fact, for cardinality constrained polymatroidal submodular maximization, this gives this famous 1 minus 1 over e guarantee, worst case guarantee. When you have constrained maximization problems, sometimes you still have 1 minus 1 over e guarantees based on a method. Like for example, here's the one we just talked about. But let's say you have one matroid constraint. If you use the multilinear extension, you still get a 1 minus 1 over e guarantee. And if you have a constant number of knapsacks, you also get a 1 minus 1 over e guarantee. And if you get k matroids, then you get like a k guarantee, and so on and so forth. You've got these different optimizations. And the thing is different when you're doing monotone maximization versus non-monotone maximization. So for example, for non-monotone in general, it's a little bit harder because you have tight bounds, the approximation in the lower bound, the hardness, for the unconstrained is 1/2, and that's known. But you get these other guarantees depending on the type of constraint. But the point is that these are feasible and actually useful. Now, for constrained submodular minimization, the bounds can be significantly improved depending on the curvature. So what is the curvature? So you look at the gain of a submodular function, and the curvature is defined as, at a set k, is equal to 1 minus the min over j of this ratio. It's kind of like the ratio of the smallest of the sort of x relative smallest gain of j divided by the largest gain of j. And then if you evaluate the curvature at v, then it's the ratio, it's the smallest possible ratio between the smallest possible gain and the largest possible gain. And this is a monotone, these are non-negative monotone submodular functions here. So everything's non-negative. And so the curvature then is going to be a number between 0 and 1. And it's called curvature because when the curvature is 1, it's like the worst case. It's kind of like, in some sense, infinitely curved. You can actually get to the point where the gain stops growing, like it truncates. When the curvature is 0, that's the same as a modular function, or everything's independent. And everything in between sort of corresponds to sort of how much interaction there is. And suddenly, as soon as you start using curvatures, so the curvature is sort of a function-specific thing. But if you partition the set of submodular functions into equivalence classes, and within each equivalence class you have constant curvature, then the bounds suddenly become curvature dependent. So oftentimes, and this is actually true, like sometimes you'll run the greedy algorithm and you're saying, well, I'm doing much better than 1 minus 1 over e. Why is that? Maybe it's because your submodular function is not so curved. So the guarantee for the greedy becomes 1 over the curvature, 1 minus e to the negative curvature. So if the curvature is 1, of course, then we get the 1 minus 1 over e guarantee again. But if the curvature is 0, then suddenly the bound becomes, 1. So we can do it exactly. And for other types of constraints, the curvature, if you bring curvature into the picture, the bounds improve. Now, for constrained minimization, curvature also seems to be a fundamental complexity parameter for submodular functions. The types of bounds you get looks a little bit complicated, but if you think about it, it's actually not so bad. So what you get is star x is the optimal solution, and the bound you get has this particular form. So let's just quickly zoom in on this. First of all, note that if the curvature is 0, then what you get is a bound of 1. But as soon as if the curvature is 1, then the bound becomes pointless. Right? But if the curvature is somewhere in between, then eventually, as the size of the optimal solution gets bigger and bigger, the bound approaches a constant because you've got the size of the optimal solution both in the numerator and in the denominator. So this basically is sort of interesting because it means that if the size of the optimal solution grows with n, that as your ground set size grows, your bound is going to get better and better. It's going to become more and more like a constant. So curvature when you bring curvature into the picture, it suddenly makes your bounds potentially much, much better. And so you have all these different bounds for these different constraints. There's cardinality lower bounds, spanning trees, matchings, ST paths, ST cuts. And when you compare the curvature-based bound for like a semi-gradient approach and the curvature-independent bounds, you can see that depending on the curvature, sometimes the curvature-based bounds are much better because all of the non-curvature-based bounds are n-dependent. And so as n grows for a fixed curvature, as long as the optimal solution grows with n, the curvature-based bound is going to get bigger or get better. OK, so that's the end of the optimization section. I want to give you a little bit of some hints as to where you can read next. So the sort of three fundamental papers on submodularity, I think, are these three. There's Jack Edmonds' original paper from 1970. There's the Nemhauser-Wissler-Fischer paper from 1978, which first introduced the 1 minus 1 over e guarantee, and Lavas's paper from 1983. And I think, interestingly enough, even though these papers are rather old, they're still very, very modern sounding and very fresh sounding. And so I think one should at some point read them all if one is interested in studying submodularity. Fujishiki has sort of written the book on submodular functions. It's a very dense book, but it's got an enormous amount of information in it. Every sentence is relevant. I mean, there's a wealth of information in every sentence, literally. And there are a number of other really nice books. Narayanan has got a book on submodular functions and electrical networks, but he's got a number of chapters just on submodularity that are very nice. There's some very good books on matroid theory and some recent books on matroid theory. Oxley's 2011 book in particular is nice. Gene Lawler's book on combinatorial optimization and matroids, that's a relevant text. Shriver has this massive 3-volume book on combinatorial optimization, which is it's an amazing achievement for a single human to do. I mean, it's amazing because every single topic also has a complete history going back to like the 1730s on that particular topic. It's a truly amazing book. And then Grunbaum has got this really nice book on convex polytopes, which gives you good background material. For those of you interested in sort of more of a machine learning slant to submodularity, I mean, all of the proofs, like I said, for every single one of the theorems that we talked about are in my class slides. So if you don't want to watch the videos on YouTube, which are available, you can just go to the class webpage and then go to the, I try to keep an index, and you can get to that proof that you want. Andreas Krause has got a nice webpage on resources for submodular functions in machine learning. And Steffi and Andreas also have a nice tutorial that they give at ICML last year that talks a lot about applications as well. Some of the applications I didn't get a chance to talk about yesterday. Francis Bach has got an updated text from last year on talking about convex structured norms based on the Laplace extension and also convex minimization strategies for doing submodular function minimization. And then for general purpose submodular function minimization, I would recommend looking at Tom McCormick's paper. And also a couple of years ago, there was a nice workshop at Georgia Tech that there were a lot of nice slides there. And a lot of people came and talked about some very, very recent work on submodular functions, some of which is very, very related to machine learning. And so with that, I would like to say thank you very much. I hope you enjoyed the tutorial, and I hope you enjoyed the whole machine learning summer school. We're almost at the end. So thank you very much. And are there any questions? So.